Okay, so we have identified 4 capacitors associated with every MOS, and those capacitors were CGS, which was connected between the gates. Then we have the CGD between gate and drain. We have DB between drain and the bulb, and the fourth one is CSB between source and the bulb. And depending upon the texture of that particular configuration, sometimes we can get rid of some of the capacitors, not all, but few of these. Now today we will look into the detailed analysis for 3 different types of amplifier, like the common source, common gate, common drain, and obviously the cascade amplifier. Now if I consider this common source amplifier, as you know, for common source the source is connected to the hard ground. Therefore, and obviously since it's incorporates NMOS device, so therefore the body is already connected to AC ground. So therefore, what we find that between source there is no such capacitor. We have one capacitor between gate to source, another capacitor between drain to bulk, and the third one between gate to drain. And out of that, this gate to drain, this capacitor experiences mill effect. Okay, so now once again let me draw. So this has been drawn already. The corresponding small signal model. You have this between gate and source. This voltage is V1, and you have a voltage dependent current source present over here, GM_V1. You should have another resistance R0 to be present between the drain and the source. And then what else? We have this capacitor CGS between gate to source or gate to ground. You have this capacitor CDB between drain to body or drain to source, because source and body they are connected together. And RD, that resistance was from the drain terminal to VDD, that is supply. So drain to AC ground, you have this resistance RD, and the input signal is having some internal resistance RG, and the input is between gate and the ground. So this is, and obviously the CGD, that capacitor is obviously present between the gate terminal and the drain terminal. This capacitor will experience the mirror effect. Okay. So now if you perform the circuit analysis at node X, what I get? So this is your node X. This is node X. So at node X, you have 3 different components of the current. One is this current, second one is this current, third one is this current. So if this voltage is V1 over there, 1 minus V in by RG plus V1 SCGS, that current, plus V1 minus V out in VGD, that is equal to 0. I am assuming that all the currents are leaving this, like this. Okay. And then if we perform this KCL particular node Y, then once again you have 4 components: this current, this current, this current, and this current. So from where we get V out minus V1 into SCGD, that means this current, plus GM_V1, this one, plus V out multiplied with the corresponding. So that is equal to 1 upon, so RD is there, CDB is there in parallel, so they are added together. So 1 upon RD plus SCDB, that is equal to 0. So from where, so V1 is your dummy variable that you would like to substitute. So do some calculation, then what we get, V1 can be represented by this form. V1 is equal to 1 upon GM minus SCGD multiplied with that particular thing, is RD SCDB plus SCGD. Now once you get this V1, and already you have this V1 in the function, V1 minus V in upon RG. So if you just replace V1 with this one, then ultimately what you are getting is this one. So I am not going to the detailed calculations. So finally we have arrived at this point. V out upon V in is minus GM into SCGD times RD by this entire thing. Now already have seen that if you just neglect the effect of the capacitor in the last unit, so at that point of time, what was the expression for the so minus GM_RD. So obviously you have this, so if you consider that, okay, this capacitor is not there, so in that case it is minus GM_RD, and obviously denominator now you have the notion of few poles, right? The denominator of the notion of few poles. So in this particular form, some A square plus BS plus 1. in that particular form. So I can write this expression, this h of s. This h of s can be represented as, this h of s is nothing but V out s by V in s. That means the effect of the capacitors are taken into account, and this is presented like the ratio of two polynomials, the numerator polynomial and the denominator polynomial. Now if you equate the numerator to 0, then what you get is the zeros of that particular transfer function. And if you equate the numerator to be equal to 0, then you'll be getting the corresponding the poles. Right? Now this ds can be represented as, in that particular form, 1 plus s upon omega multiplied with 1 plus s upon omega p2. That means what? You have an expression like this. You have this d of s, this denominator polynomial, can be represented in this particular form like a of s square of s plus 1. That is the form, and you can also represent this 1 plus s upon omega p1 multiplied with 1 s upon omega p2. Now what is the implication of omega p2? These are the two corresponding pole frequencies, right? And you have two unknowns there, omega p1 and omega p2, and you have this equation a square plus bs plus 1, right? So what you need to do is you have to equate the coefficient of a square, that is a here, and what is the corresponding coefficient? Nothing but 1 upon omega p1 omega p2, right? What about the coefficient of s? That is nothing but b, right? Which is equal to 1 upon omega p1 plus 1 upon omega p2. So you have two equations. So from that you have to find out this omega p1 and omega p2. Sometimes omega p1 might be larger with respect to omega p2. In that case, you get an idea regarding the bandwidth of that particular amplifier cell, right? Now whenever you encounter one such pole frequency, what is the implication in the frequency response? Suppose you have 1 plus s upon omega. Now when s reaches this omega p1 value, what will be the implication in the corresponding transfer function? What do you expect? What do you expect? Any idea? You have two unknowns here. Two unknowns. One is this one. One is this one. That is the coefficient of s square. And the second one is this one, the coefficient of s. Right? And you have to find out from these two unknowns, you need to find out the corresponding pole frequencies, omega p1 and omega p2. This omega p1 and omega p2, then you'll be able to find out the corresponding transition point at which the roll off. Initially, when s is very small, once again let me just consider that particular formula. Like, let's assume that h of s is given by 1 upon 1 plus s by omega p1. Suppose you have only one such pole frequency, 1 by 1 plus s by omega p1. Now when s is very small, low frequency, obviously you understand the nature of that particular transfer function. Is it a low pass filter, high pass, band stop? What is your idea? Low pass, right? Or you can also write like, what is mod of h of omega? That is 1 by square root of 1 plus omega by omega p1 whole square, right? 1 by square root of 1 plus omega by omega p1 whole square, right? So when omega is very small, that mod of h omega, I have just normalized this one, so that is equal to unit. Now as omega approaches omega p1, then what is the value? 1 by root 2. 3 dB decay. Then what about the corresponding change? Minus 20 dB per decade. That means what? If omega Suppose initially your omega value is equal to some value. Suppose initially omega is equal to some omega dashed. And then the omega becomes 10 dashed. That means you have increased the frequency by 10 times. Right? In fact, what happens to the corresponding transfer function? Minus 20 dB. That means with respect to the corresponding magnitude value at omega is equal to omega dash, when the omega is increased by 10 times, right, then the corresponding function, the magnitude, decays by 20 dB.
But sir, if omega dash is very, very small as compared to omega b1, then the value will be same.
That is an approximation.
But omega dash or 10 omega dash and মাঝে omega b1 dash. কারণ যদি omega 10 omega dash যদি omega b1 থেকে অনেকই কম হয় তাহলে তো
obviously. And once you follow this particular procedure, you'll be having some approximate behavior. If you can remember, I think you have already studied this Bode plotting LCS also, right? And so it will give you the notion of the approximate behavior of the transfer function. Once you have this particular, once you have this expression, that is the exact expression, because you have got this particular small signal model in all the parameters, incorporating the resistors, incorporating the current source, incorporating the all the capacitors, and then what you have done, you have just applied the basic circuit law, KCL and KVL, and from which you have derived this expression. So this expression, now suppose given that particular expression, you are asked to draw the small, I mean the function as a function of the frequency. You are asked to draw the frequency response as a function of frequency. Will it be easier for you? No. That's why what we are doing, we are adopting that particular Bode plot. What is our idea? Our idea is to identify the corresponding signal node. How many signal nodes are there in the circuit? There are two signal nodes, one at the input side, second at the output side. And then you have to find out what are the corresponding resistance, particular node to ground, and what are the corresponding capacitance from that particular node. Based on that, you have to find out the corresponding RC time constant, and once you get the RC time constant, then you know that this corresponding omega, what is omega expression? Omega p1, suppose input side you have some omega, that is, let me call it like omega in, or omega p in, pole frequency omega p. What is that omega p? That is nothing but 1 upon yeah, 1 upon RC. Effective R effective, C effective, the input side. Similarly, the output side you have such like what is that? 1 by R out effective, C out effective. So you need to, so once you identify those nodes, so let me move to that particular analysis. This is the exact expression, exact calculation. Yeah. Now this one. Yeah, this one. Right. Now already you know that this is my circuit. The circuit looks something like that. You have this circuit now. You have this circuit. This is basically supply. This one is RT. This is RC, right? So you have one capacitor. What is that one? As CDB. Here one capacitor, here to here, here to ground. What is that? CGS, right? And then one capacitor connected between gate to drain, that is CGD. Let me decompose. One between here to ground. Let me call CGD out. And one capacitor from here to ground. Let me call CGD in. Okay. Clear? Then what about your CGD in? If you just follow the Miller theorem, what is 1 minus A times 1 minus A times CGD is A. For this kind of circuit, you know that the expression for A is the mid-band gain minus J. We have already calculated this one, minus GMRT. Mid-band gain for a simple common source amplifier with a resistive load. That was the expression, minus GMRT. So this effective capacity input side CGD in is nothing but 1 minus A times CGD, that is 1 plus GMRT times CGD. So let me decompose this CGD into two parts. One between the gate to the ground, that is this one, 1 minus A times CGD, that is 1 plus GMRT times CGD. Already you have this RG, I mean the source resistance, you have this input signal V in, you have this CGS. Input side is over, right? Output side, you have this GMV, CDB, RD, this CGD, because the corresponding decomposition is nothing but 1 minus A inverse times CGD. Since A is large, so A inverse can be approximate to 0, so it is close to CGD. So there is no such magnification at the output side, as you already studied. Okay, so now these are the 2 points. This is one node over input side, this is another node. Now you have to find out the corresponding resistance value and the corresponding capacitance. What about the resistance over there at the input side? RG only. What about the effective capacitance at the input side? The summation of these two capacitors are there. So effective will be CGS plus 1 plus GMRT times CGD. Right. Now coming back to the output side, what is your RC out? If R naught is there, then you can also incorporate this R naught in parallel, because you know since RD is present, the effect of R naught will be simply neglected, because R naught is much larger as compared to RD. So what you can do, okay, if you place some RT R naught over there in parallel with this, you can always place some R naught like this. R naught you can also place in this will be RD parallel R naught. Right. But this is close to RD since R naught is large. Okay. So RC out is going to be RD into CD plus CG. Now looking at these two expression for RC in and RC out, you tell me which one is larger? Which RC is larger? Which RC is larger? You have this Miller magnification present, 1 plus GMRT. So the upper RC is larger. Therefore, which pole frequency is lower? So omega P is equal to 1 upon RC in, and omega P out is 1 upon RC out. Since in is larger as compared to RC out, therefore omega P in is smaller as P out. Therefore, whenever you increase the frequency from 0, at omega P in rarely as compared to omega P out. Now once you reach at omega P in, right? Once you reach at omega P in, there is, once you reach over there, then you have a 20 dB decade, or 20 dB fall per decade, right? And then you reach at another omega P, that is omega P out, right? First you reach at omega P in, and then P out is larger as compared to omega P in. So you have 20 dB per decade, another 20 dB per decade. That means now it becomes 40 dB per decade. Minus that because it is. Now once you encounter a zero frequency, what will be the corresponding impact? If you encounter some zero frequency, no, if you encounter frequency, plus 20 dB per decade, right? If you have some zero frequency, then plus 20 dB per decade. So this one is much larger, because once we just take a look at the zero frequency, what is my zero frequency? What is the value? GF minus SCG equal to 0, right? Then what is your corresponding omega value? GF, right? Is it small or large? This omega?
GM is very large.
GM upon CGD, omega. Okay, this has been already explained over there, as I've told you. Yeah, that part I think we have discussed last day. No, the mathematics was not discussed.
one minus a করছি তাহলে আমাদের common drain আছে আমরা তো এখন a এর ভ্যালু 1 হয়ে যাবে তাহলে 1 minus 1 0 হয়ে যাবে
We have not discussed common draining. In case for your common drain amplifier. Yeah. Yeah, it's common. Yeah, I'm coming to that. It's a common drain. Let me discuss. It's a common drain, right? So let's start with 4 capacitors: CGD, CGS, CDB. And there, what we have used, we have instead of having a simple resistor between the source and the ground, which is acting as your output resistance, we have biased this using a ideal current source. If you have ideal current source, that means infinite, right? So out of 4, between gate to drain to body, drain is connected to what? Drain is connected to VDD, that means AC ground. Body for MOS is connected to DC ground, hard ground. Therefore, CDB will not be there. What CGD? What about CGD? Last time, that gate capacitor CGD was experiencing Miller effect last time, or common source, right? Which was connected between the gate and the drain. That time, your gate was acting as the input, drain was acting as. But this time, drain is acting as DC ground. So CGD will be there between gate to, right? What about CS? What about CSB? Will it be there or not? Will it be there or not? It will be there. What about CGS? CGS? Gate source? থাকবে. Both of them are signal points. Gate and source. One is input, second one is out. Now, if you draw the small signal model, what you are getting? First of all, you need to draw the. Okay, let me just mark. Yeah. So this is your gate. This one is source. This one is drain. Drain is connected to AC ground. Drain is connected to AC ground, so we have used that. Okay, lambda is equal to 0. That means there is no channel length modulation, and also gamma is equal to, that means there is no body effect. Although this particular circuit experiences body effect, and obviously it will experience some channel length modulation. Okay. So out of 4 capacitors, already we have seen that okay, one will not be there. Only you have the CGD, CGS, and CSB. So CSB will be there between body. CGS will be there between gate and the source, and CGD will be the gate and the drain, and drain is grounded, AC ground. Okay, we apply the KCL at this node at the gate end. What about this voltage? What will be this current? This current plus this current. This current equal to this current, right? So what is this current over here? What about this voltage? Voltage at node X. What is that voltage? At node X, what is the voltage? Exact voltage at node X. X to Y, difference is V1. And Y to ground, it is V out. X to ground, what is the voltage? V1 plus V out. This voltage V1 plus V out, this one. Here to here V1, and here to here V out. So this voltage is V1 plus V out, so this is V in. Current flowing through this, V in minus this voltage Vx, that is V1 plus V out upon Rg. This current is entering. Suppose it is divided into 2 segments. One is through this one, CGS. This current, this difference is V1. This capacitor is CGS. What is that current? It should be V1 times SCGS. That current. Okay. And once again, as you understand, this voltage is V1 plus V out, and you have CGD, this capacitor. V1 plus V out times SCGD. So you have applied KCL in node X. Then another signal node at node Y. And over here, now you have this current plus this current equal to this current. Right? What is that? Okay. So GMV1 plus V1 SCGS, that is equal to the current flowing through CSP. That is V out into SCSP. From here, you can represent V1 in terms of V out. Right. And then you just plug in of V1. V1 is equal to this one. Just plug in this value in that expression, the first expression. V in upon Rg is equal to V1 plus V out upon Rg plus this expression, entire expression. And now if you just plug in the value of V1, then you can represent this entire expression in terms of V in and V out. Yeah. So V in upon Rg equal to this entire thing. So you take V1 common, 1 upon Rg plus SCGS plus SCGD over there, and if you take V out common, then 1 upon Rg plus SCGD. Already you have represented V1 in terms of V out, SCSB plus SCGS times V out. You just substitute this value over there into this expression. This one is remained as it is. Simple calculation, nothing difficult. Yeah, finally, this expression. Second order system, NS, PS. You have 1 0 over there and 2 poles. Yeah. This one. It is a common gate. Common gate, yeah. Do it. No harm. Just do it. You have a resistance now, RG. You have one resistance on the input side. Get resistance. This one is V. Some current source related by I1. V out. Okay. CSB. Okay, CD will not be there, I'm not drawing. What else? CGD. CGD. And then the CGS is having two components. So CGS was connected to the gate and the source. So what we have? Let me connect here. Now, if I consider, okay, let me write like this: CSB. CSB. What is the common terminal? It is not what is the common terminal. You have a CGS was present between the gate and the source terminal, right? CGS was present between the gate and the source. Now, both of these two terminals, both gate and source, they are the signal nodes. None of them are connected to some constant voltage, either DC ground or AC ground. None of them are connected. Both of them are signal points, right? So, whenever I am decomposing, method of decomposition for your common source, what you have done? You have identified that gate and last time gate drain. These are the two signal nodes, gate point and drain, and so your common point, the common terminal was the source terminal. From gate to source, the source is a reference terminal. Source was a reference terminal, and you have one capacitor which is connected between the gate and the drain. So you have divided this one in between gate and the reference terminal and drain and the reference terminal. That was the idea. Now this time the capacitor is connected between gate and source, which experiences gate and source which experiences the mirror effect. What is your terminal here for common drain? Drain. Right? So therefore, what you need to do? You have to decompose this capacitor CGS. One between gate and drain, second one between source and drain. Can you experience any capacitor between source and drain? Between gate and drain? Already have some capacitor, and that effect you can incorporate within the CGD. Can you get the point? That effect you can incorporate within CGD because already you have the capacitor between gate to drain. Now, what was that capacitor? So that capacitor was there between, let me use a different color here. So that capacitor was there between gate and source, CGS. Drain is the reference terminal. So I have to put this capacitor into two parts, one between gate and drain, and second one between source and drain. Right? Even if you consider drain is connected to AC ground and the body is also connected to AC ground or DC ground for MOS, body is always connected to your AC ground or DC ground. So therefore, this CGS capacitor, which experiences Miller effect, that goes into two different segments. One between C, G, B, and the second one is C, S. Instead of writing B, because since it's connected to AC ground, so I can also write it like C, S, B. Now that CSB, some CSB over there between source and the bulk. In the bulk, you have already one capacitor. So because of the Miller effect, you don't have any additional capacitor. Out? There should be one reference terminal. For common drain, your reference terminal was drain. And the capacitor which is experiencing the Miller effect, was C, G, S. Right? So, and drain is a reference terminal, common. Drain common. So therefore, I have to segregate this into C, G, D, gate to drain, and already you have one capacitor there between gate and drain. What about this? The other one, between source to drain. Between source to drain is already connected to AC ground. You can also consider, okay, this is nothing but your C, S. Drain and body, they are connected. AC wise, they are connected. And also the CSB is already there. So once you convert this Miller effect into a calculation or approximate calculation, you have another capacitor to work with, because both this CGD and CSB are already there in the circuits. Right. Okay. So I think my today's time is already over. So let me stop here. Today we have discussed the common source and the common drain today, and we have to work with the common gate, this one, and this cascade amplifier, the effect of this cascade amplifier in the next class.